All right, so continuing our notes from yesterday. So again, it's going to be a short lesson today, and we'll pick it up tomorrow after the quiz. So on topic 1, we ended with arithmetic sequences. So today we're going to do the other type of sequence. So if you go to page 4 in your notes, starting with example 6, we're going to look at what's happening recursively from one number to the next. So from here to here, it might be easier to start with the whole numbers. So notice from the first to the second, I'm adding 3, but it doesn't continue adding. This one, it's a multiply sequence, so we're multiplying by 4 to get the next one. And if we tried the previous one, 1/16 times 4 would give us 1/4. 1/4 times 4 gives us 1. So the pattern is that we're multiplying by 4. So again, the recursive, if I want the next 3 terms, so this is a 1, 2, 3, 4, 5. So it wants a 6, a 7, and a 8. So to get a 6, you take the last one over here, which was 16, multiply by 4. So times 4. 16 times 4 is 64. Times 4 again. And we get 256. And multiply by 4 again. And that's 1024. So again, recursively in order, we multiply by a number. And again, just like the other one, it's going to have an explicit, but that one you have to know the formula. So we'll get to that in a second. This sequence is called a geometric sequence. Because each term is determined by multiplying a non-zero constant to the previous terms. So if we're dividing, it also includes dividing, but dividing is just multiplying by a fraction. All right, so here, the number that we consecutively multiply by is called the common ratio. Because to get it, we're going to divide 2 numbers to get that common ratio. All right, so just like we did for arithmetic, we're going to have 2 different formulas, a recursive and an explicit. So the first part is the recursive formula. So reviewing what recursive means. So again, you start with the first one. So we still have a sub 1 is the number. And then we take a sub 1 to get the next term. So you take a sub n to get the next term. You take the previous one, n minus 1, and you multiply that by the common ratio. So labeling stuff, this first one is the first term. Whichever one your first term is in the sequence. To get the next one, the one that you want, you take the previous one. So a sub n minus 1 is the previous term. And r here is the common ratio. So this one wants the first 5 terms in the sequence. So write the first 5 terms. So again, I find it helpful to write the spaces 1, 2, 3, 4, 5. So a sub 1 is the first term. So this one goes here, 1. And then to get the other ones, we consecutively multiply by the ratio. So in this case, the ratio is 3. So times it by 3, and we get 3. Multiply 3 by 3, and we get 9. Times 3 is 27. Times 3 is 81. So again, let's prove with this formula. The formula actually flips the ratio and the previous term around, but it doesn't matter because multiplying, you can switch them around. So to prove a sub 5, so a sub 5 is the previous one, well, we'll use this formula. 3 times the previous term is a sub 4. In our picture, or in our sequence, 1, 2, 3, 4 is 27. 27. And 3 times 27 gives us the 81 that we got there. So again, that's just the proof on how we get the number using the recursive formula. So looking at B, again, start with A1. So A1 is 162. This time, our common ratio is 0.5. So we're going to multiply by a half each time. Multiplying by a half is the same thing as dividing by 2. So we're just going to take these consecutively and divide by 2. So 162 divided by 2 is 81. 81 divided by 2 is 40.5. 40.5 divided by 2, 20.25. And then divided by 2 is 10.125. So it's okay to leave decimals like this, but if they were repeating decimals or they got too big, then I would definitely change it to fractions. All right, so that's the recursive idea for the sequence. For a geometric sequence, pretty much the same as an arithmetic. So now let's look at a couple of sequences and tell if they're geometric or not. So for the bottom part, determine whether each sequence is geometric. If it is, then write the recursive sequence. So for it to be geometric, it's got to be a common ratio from one to the other. So here, -2 times what is 6? -2, negative and a negative makes the positive 6, and 2 times 3 is positive 6. So multiply by -3. So I'm going from a positive to a negative. So -6 times 3 is 18. A negative to a positive, so it's got to be a negative again. And 18 times 3 is 54. So because the ratio is the same, then we can say yes, it's geometric. And let's say yes or no over here first, and then we'll come back and write the recursive. So going from one to the other, here I would multiply by 2 to get 8 to 16. And then from here to here, I know it's not 2, because 16 times 2 would be 32. But to figure out the exact number, you just divide. 24 divided by 16 is 1.5. So right there, since those are not the same, I mean, you could do this one too, not the same. We would say that this one's not geometric. All right, so for the geometric one, we write the recursive. A sub 1, the first term, is -2. And then to get every other term after that, we take the previous term and -1. And in this case, instead of adding or subtracting a common difference, we multiply by the common ratio, which is -3. For a lot of these, putting the negative and putting fractions in parentheses is going to be helpful. Not that we need it here, but once we start making the explicit formula, we're definitely going to need the parentheses. All right, a geometric sequence is an exponential function. And this is the unit that we're on, is exponentials. And later on, we're going to graph it. It's going to look like this, r to the x. R is going to be your common ratio. Right now, we're not graphing it. But this is what we're getting into. This is what this unit is. Unit 9 is exponentials.